All right, so this is going to be the last of our videos introducing the content associated with sequences. We still need to do a little bit more work with series. I also am thinking I might do sort of a summary video with sequences just because there's been a lot in the last video, and then this one is going to have a fair amount in it also. Hopefully I can keep the time a little shorter than the last one. The last one was kind of long, but I don't want to ramble too much or this one's going to be long too. So let's get into our learning objectives. In the last video, we looked at arithmetic sequences. In this video, we're looking at geometric sequences. So the first is the same learning objective as the last video. You need to be able to recognize them. So I'm just going to summarize that content very quickly in this video. Really, this main idea is in the last video. So you may want to go back, actually two videos ago, and watch that again. That video, fortunately, was relatively short. I think it was like 10 minutes if you need to watch that again, or if you haven't watched it yet. The next thing that we'll do is we'll talk about how to find an explicit formula for the geometric sequence. And when we talk about formula, again, remember what we're looking for is the formula that can be used to generate all the terms. That's what we're looking for, all right? So a quick review of lesson or learning objective number 1. So this is from 2 videos ago. This right here is from 2 videos ago. We made this little table right here. And we talked about that basically there's 2 types of patterns that we're going to study in our class. One pattern is adding and subtracting, right? Because subtracting is the same as adding a negative. So adding and subtracting. And whenever you see that pattern, that's called an arithmetic sequence. And that's what the last video focused on, of how to generate the formula for an arithmetic sequence. If the pattern is multiplying, and remember, you can always multiply by a number that's less than 1. So that would include things where the signs change because you're multiplying by a negative. That would also include things where the numbers are getting smaller because you're multiplying by a fraction between 0 and 1. Okay, so this can happen. It can look like multiplying. It can also look like dividing, and that's geometric. And this is what we're looking at in our video. As far as making the formulas are concerned, it really doesn't matter if it's a finite or an infinite sequence. Where that's going to start to come into play is when we start getting into their sums, when we get into the series of these different things. So in this video, we're going to be looking at how to generate the formula when our pattern is multiplication, i.e. when we're looking at a geometric sequence. So let's go ahead and get started. You'll remember that the key to doing an arithmetic sequence was recognizing that they act the same as linear functions. Well, there's a similar key with geometrics. So if my pattern in a geometric is that I am going to multiply every single time. Oops, let's start with 1, 2, 4, 8, 16. If this is my pattern, that I am multiplying every single time, right? If you go back and you think about the functions that we have studied, when we studied linear functions, we found that they had a pattern that the y values are going up by adding. And so it makes sense that an arithmetic sequence would act like a linear function. But we also studied functions where we found the y values were steadily increasing by a constant multiplier. Can you remember which kind of function increased by a steady multiplier? It was exponential functions. So what we're going to find is that geometric sequences will act in a way that's very similar to exponential functions. Okay, so this is what we're going to see is geometric sequences will act in a way that's very similar to exponential functions. And so we can start working with equations that look like exponential function equations. Now, when we studied exponential functions in our class, we did not talk about how to generate their equations. At least we didn't this year. Maybe in future years, but we didn't this year. COVID, right? And that's just kind of how it goes. But what we'll do in this chapter now is we'll start working with that a little bit. So what I'm going to do is I'm just going to remind you that in the land of functions, and in fact, I'm just going to do this off in the margin. You don't even have to put this in your notes if you don't want to. But in the land of functions, when we're dealing with exponential functions, you have some constant base. In this case, well, let's not worry about that. You just have some constant base, and then it's raised to a power where there's a variable. That's the basic structure for an exponential function. There's a constant base, it's raised to the power where there's available. But then we talked about you can start doing things to the function. So you can do things like add or subtract something from x, and all that does is it moves the graph to the right or the left. Or you can do stuff like multiplying the function by some numbers. I'm just going to put a for any number. And that has the impact of stretching it out and things like that. So these are the types of things that our geometric sequence will act like. But I'm not going to go as in depth as I did with arithmetic sequences, just simply because we didn't study these equations as much as we did with linear functions, which connects to our arithmetic sequence. All right. So here's what I'm going to do. I'm just going to jump to the punchline that there's going to be a basic structure associated with a geometric sequence. And that basic structure is going to look like an exponential function. Okay, it's going to look like this. But we know it's a sequence and not a function, so it's going to have slightly different notation. Like, for example, instead of having an f of x, we know it's going to have an a sub n. Of course, there'll be the equal sign. Tells me that I've got an equation, something that I can use to generate the terms. All right, now, what we're going to have is, notice I'm leaving a little space here. We're going to have a basic base raised to a power. Now, the base that you have right here, the thing that's going to be raised to the power, this thing right here is always going to be equal to whatever your pattern is, whatever your multiplier is. So in the example that I have up here, my pattern is that I'm multiplying by 2 every single time. So that means my base would be a 2, okay? So the base of the exponential term will be equal to whatever your pattern is that you've got up here, okay? Now, we do have a variable for this. To represent the pattern that we have here, we do use the variable r, okay? But it's not r standing for the rate of change, it's r standing for the common ratio. Common ratio, okay? And there's a good reason why it's called a common ratio, but we're not going to get into that in our class. All right, so just r. That's kind of a funky looking r, but that's okay. There's r, lowercase printed English r. That's what we've got here. All right, so we've got that. Now, it's going to have an exponent, and the exponent is where you're going to plug in n. Just like in an exponential function, you plug in the value for x up in the exponent. That's where your variable lives, is in the exponent. In our geometric sequence, the exponent is where my variable n is going to live, okay? And again, for reasons that we're not going to entirely go into, that would make sense if we studied exponential functions in a little bit more depth. I'm just not quite sure that we've got sufficient background to explain this. There will always be up here in the top a -1. There will always be a -1. So if you think about our exponential functions, what that means is in a normal exponential function, normally you would cross at 0, 1, right? That's normally where we would cross. But this is going to shift that to the right. So this point is actually going to move over here, and we're going to cross at something lower, okay? But that should kind of make sense, because remember when we talked about arithmetic sequences, we said that this thing back here was like step 0, and you never actually get to step 0 because our sequence starts at step number 1. Step 0 is this imaginary thing. So it makes sense that the first thing I see right here is going to be something that's moved to the right from the y-axis. Okay, now, again, we don't have a strong enough or enough experience, maybe is a better way to say it. We don't have enough experience with exponential functions to go into much more depth than that as to why there's a -1. Bottom line, what you need to remember is you need to remember there's a -1 right there. Then the other thing that happens is this whole exponential expression is going to get multiplied by something that ties into where this begins. And this actually turns out to be easier than it was with an arithmetic sequence. With an arithmetic sequence, we had to add on that step 0 business. But remember, we had to go and find it because step 0 is never given to you up here. In a geometric, what we're going to multiply by is step 1, which is very nice because if they write it out like this, you can see step 1. So that's really nice if they do that. So these are the two things that you're going to have to find, right? So you're going to have to find step number 1, whatever its value is. So in fact, let me write that. The value of step number 1, right? That's what we need to find, the value of step number 1. And then we need to find what our pattern is. And those are the two things we need to find. And once we've got those, we just write it in this particular format. And we're done. And we're done. Okay, so let's take a look at this example that I have up here. I can see what step number 1 is. Step number 1 is right here. Okay, it happens to equal 1. Step number 1, of course, doesn't always equal 1. Remember, when I say step number 1, I'm referring to the fact that this is in the first spot, this is in the second spot, this is in the third spot, this is in the fourth spot. So the thing that's in my first stop, that's step number 1. Also sometimes called, remember we talked about in the last video, sometimes called term number 1. Okay, so whatever you want to call it, term number 1, step number 1, it's the thing that's in the first spot. So in this particular example, my thing in the first spot is equal to 1. So if I was to write an equation of this, I'd have a sub n equals, because remember that part's always going to stay there, my first term is a 1, and then I'm going to multiply that by something that represents the pattern I have. So up here, we said my pattern is I'm multiplying by 2, multiplying by 2. Every time I multiply by 2. And so that's what would go here is a 2. And then I've got an exponent, and the exponent is always going to be n minus 1. That's always going to be my exponent, is n minus 1. And so this would be the equation of that particular geometric sequence. I would say maybe this is, I guess, is a little bit up to you. We know that anytime I multiply a thing by 1, and remember, I'm multiplying this whole thing by 1, so I can't multiply 1 times 2. It's this whole thing multiplied by 1, because order of operations, exponents come before multiplies, right? But anytime I multiply by something by 1, I just get the something. So this exponential times 1 is just going to be equal to the exponential. And so I might write my answer like that for this particular problem. But generally speaking, there's going to be a 1, or I'm sorry, not a 1, but some number out in front of your exponential, generally speaking. Okay, so this is the basic idea. This is the basic idea. Now what I'd like to do, like we did with the arithmetic sequences, is take a look at a couple of examples. We kind of just did the easiest type of an example where there's just a list of numbers where you can see what the first term is, and you can see what the pattern is very easily. So what I want to do this time is give you another type of an example, like we saw in the arithmetic sequence video, for finding a formula. And remember, sometimes it's called an explicit formula. Some textbooks even call it an explicit definition. Okay, I tend to not use that terminology myself, but some call it that. So find the explicit formula of the geometric sequence in which the second term is equal to 8. And the sixth term is equal to, just a second, 648. Okay, now let me pause real quick before we go too far into this. Your initial thought to this is, wow, 648. I mean, we're kind of going big all of a sudden, okay? Here's the thing, with exponential sequences, I'm sorry, geometric sequences, exponential functions also, but geometric sequences, remember we saw the numbers change very rapidly. And so you're gonna run into situations where you've got big numbers over here, or maybe small numbers, really tiny decimals and fractions might happen. Bottom line, you're going to end up with numbers that are just simply not pretty, not convenient. And remember when we talked about this in the last video on an arithmetic sequence, when the numbers are big and not convenient, a lot of times what we're going to want to do is we're going to want to use formulas. And so I want to take advantage of this particular sequence right here to generate two formulas that we can use to help us figure out what R and what A sub 1 are going to be, right? So we know our basic answer is going to have this structure. And me personally, when I'm doing problems that ask me to find a formula or find an equation or anything like that, I always start by writing down what my answer is going to look like. So I always start by writing down that basic structure, the basic formula that I'm going to use. Okay. Now I know these are the two things that I need to find. I know that. Everything else is going to stay as a variable because it needs to be able to represent all the terms in the whole sequence. So these are the two things that I need to find. Just like we did with geometric sequences, we're going to find that 99% of the time, our life is easiest if we find the value of R first. We're usually going to want to find the value of R first. Okay, so let's start like we did with the arithmetic sequence by looking at a visual of what this thing is. So I've got this thing that has at least 6 terms and maybe more. Okay. And we don't know for sure if it goes forever or not, but it doesn't matter when it comes to making the formula. So it's got at least 6 terms. So here's my first term, here's my second, here's my third, here's my fourth, here's my fifth, here's my sixth, here's my seventh. And the terms that I know is I know term number 6 is 648, and term number 2 is 8. Those are the 2 terms that I know. All right, so let's think about what's happening. One thing that I see that's happening is my numbers are getting bigger. So that tells me I must be multiplying by something that's bigger than 1, right? Because if I was multiplying by like a half, my numbers would be getting smaller, not bigger. So I also know, because it's geometric, that I'm multiplying. I guess maybe that's the important place to start. Because it's geometric, I know that I'm multiplying. So I'm multiplying by some constant thing that I'm calling R. So I multiplied by R once to get to here. And then once I figured out that answer, I multiplied R again to get this answer. And then I did it again to get this answer. And then I did it again to get this answer. So I multiplied by R in this particular case 4 times. In this particular case, 4 times. Okay. Now, we did something like this when we talked about arithmetic sequences, and we indicated that you know how many times you're doing this process based on recognizing how far apart your 2 terms are, right? So if I know that I'm going from term 2 to term 6, then just subtracting here tells me how far I've gone. Okay, so that's the first piece. Now, for the next piece, I need to figure out what's the value of R. Well, if you remember what we did with arithmetic was we could just subtract, right? Or I'm sorry, we could just divide, right? If you add something over and over and over again, you divide by how many times you add it. Well, with multiplying like this, I can't divide. I've got to take it one step up. So what I'm going to have to do is I'm going to have to use a radical, right? Because what I've got here literally is I have 8 times R again, times R again, times R again, to get 648. That's literally what I have. So I've got 4 of these R's multiplied together. That's the same as having R to the 4th power. Okay, so notice what I've got. The number of times that I've multiplied, that became my exponent right here. And then my 2 numbers are my 2 numbers. So I can just solve this equation. First thing I'd have to do is divide both sides by 8. So that gives me R to the 4th equals, I'll grab my calculator in a second. I'll figure out what that is. But I want to leave it like that for a minute. And then I'm going to have to take the 4th root of both sides. The 4th root of both sides. Okay, the 4th root of both sides. All right. And then this is what I'll need to simplify. So I grab my calculator, and 648 divided by 8 gives me 81. And then I'm going to take the 4th root. And remember, on your calculator, there's 2 ways to do the 4th root. In the math menu, there is a way to get any sort of root that you want. It's option number 5 in your math menu. My personal preferred method is I like to just take the number and then raise it to a power where I turn the fourth root into a fraction. If you remember, we did that last semester. So in this case, my fraction would be 1/4. So 81 to the 1/4 power. That's the same as the fourth root. Okay, so whatever way you prefer to take the fourth root, but there we go. All right, so there's my basic process. Now, you can go through, just like we talked about with an arithmetic sequence, you can go through this exact process where you're writing things down and you're counting and you're doing all this stuff every time, and that's fine. But what I want you to notice is there is a basic pattern that you can use that doesn't ever change. Let's think about where the different pieces of this equation came from. The two numbers inside my roots, 648 and 8, where those are coming from they're coming from the two terms that I was giving. So I was given term number 2 was equal to 8, term number 6 was 648. That's where these two things are. So what I'm going to do here is write a little equation that works, generally speaking. But I'm going to use it with some variables. So I'm going to say using term, let's say, I don't want to use A's. Let's say term M and term N. Okay, I don't like M either. That's a bad term. Let's go M and P. M and P. Term M and term P. Okay, I don't want to use term N because I don't want to get confused with this. Okay, so let's use term M and term P. So in this case, the two terms that I'm given, I'm thinking of this as being term M, and I'm thinking of this as being term P. That's what I'm thinking of. Okay, so the way that I got the index for my radical was based on knowing how many times I multiplied R. And I could figure that out by subtracting which two terms that I had. So in this case, I had a term 2, a term 6. If I think of these as being terms M and P, that just means I'm doing P minus M. P minus M, 6 minus 2, P minus M. That's what I'm working with. So R is going to be equal to some radical, and the radical is going to have an index of P minus M. That's going to be my index, P minus M. All right. Now, I had the two numbers inside of my fraction, or inside of my radical, the two numbers inside of my radical that make this fraction. The number in the top is the actual value of a sub 6, or in this case, a sub p. So the number in the top is the actual value of a sub p. And the number in the bottom is the actual value of a sub m. And so that becomes my formula. Now, if it helps you as far as typing it into your calculator goes, you could write it instead of as a radical notation, you could write it as an exponential notation, if that helps you, by just making it a 1 over P minus M. Okay, 1 over P minus M. So that's the way that I typed it into my calculator, right? 1 over 4, right? And 4 came from doing 6 minus 2, P minus M. Okay, so this is a formula that you can use to figure out what R is equal to. All right, now to figure out the rest, we just plug something into the equation. So if I know that R, in this case, R is equal to 3, I need to figure out a sub 1. What I can do now is just plug in one of the points that I know. So I always pick the point that just has the easiest numbers, and I think 2 and 8 are easier than 6 and 648. So I'm just going to pick this one. Okay, so this was term number 2, so n was equal to 2, and the answer was 8, so the answer was 8. And then I would just solve this equation right here. So 2 minus 1 equals 1. 3 to the first power equals 3. And now if I want to get a sub 1 by itself, I just divide both sides by 3. And 8/3 is the value of a sub 1. Okay, so I've got my answer to this problem, or I have everything that I need. But let me make sure that we kind of summarize, what did I just get here? What I just did by plugging those two numbers in is I ended up with a sub 1 being equal to one of the terms divided by the common ratio raised to this power right here. Okay. Now, you can, if you want to, just like I did here, start with this equation every time and solve it. And that's perfectly fine. Or you can just realize what I'm going to do every time is just take the value of this term and divide it by that every single time, right? And that's going to get A1 by itself. So finding A sub 1 using a term, whatever term you want. In this case, I chose to use AM. You could just as easily use AP. It can be any term that you want. I'm just going to write AM because that's what I used. Then A sub 1 is going to be equal to the value of AM divided by R raised to the n minus 1 power. Okay. And that's going to give you the value of A sub n. Right? So these are our basic formulas. This is an example where we did not use the formulas because the numbers were small enough and straightforward enough that we could work through it logically. But as we work through it logically, these formulas just happened. Okay, they just happened. So you can choose, work through a problem logically like I've done here, or just jump straight to the formulas. Just simply jump straight to the formulas, right? And that works too. So this video is already fairly long. I think I'm going to stop it, even though there's only one example. What I will do, I believe, is make a final video. I suppose it's somewhat optional to watch, where we just do an example using the formulas straight up. All right. So I hope this helps. Thanks for watching. Have a good one.